When we talk about PLGA-based injectables, the first thing that comes to mind is their incredible promise for long-acting drug delivery. But behind that promise lies a world of complexity, one where stability issues can make or break a formulation. In today's session, we're going to explore why PLGA stability is so challenging, and more importantly, what you can do to overcome those challenges with science-driven strategies that actually work. Let's start by understanding why PLGA is so challenging to work with. On one hand, PLGA gives us everything we want. It's biodegradable, biocompatible, and completely customizable. But the same properties that make it versatile also make it unstable under certain conditions. Stability in PLGA injectables isn't just a chemistry issue, it's a systems issue. Hydrolysis, moisture exposure, processing conditions, and even the drug molecule itself all interact throughout the product life cycle. And if even one part of that system is off balance, your entire release profile can shift. Hydrolysis is the #1 stability challenge in PLGA formulations. PLGA naturally absorbs water, and water breaks the ester bonds in the polymer chain. This isn't a flaw, it's the exact mechanism that makes PLGA biodegradable. But in injectables, this process can move much faster than we want. As the polymer breaks down, it creates acidic byproducts. That results in faster degradation, internal acidic microenvironments, unexpected burst release, and in many cases, direct instability of the API itself. To control hydrolysis, there are 3 strategies that consistently work. First, choose the right monomer ratio. 50-50 PLGA degrades the fastest, while 75-25 and 85-15 grades slow things down. Picking the right ratio is one of the easiest ways to tune release duration. Second, adjust the end group chemistry. Ester-capped PLGA absorbs less water and slows hydrolysis, while acid-terminated grades speed it up. And third, manage moisture carefully. Even a tiny amount, 0.1% moisture, can shift the release profile. Using dry polymers, dry solvents, and dry processing steps is essential. These 3 adjustments alone can rescue many PLGA formulations that look unstable at first glance. Now let's talk about the drug itself. When PLGA degrades, the pH inside the particle can drop below 5.0. And if your API is sensitive to acidic environments, things can go downhill fast. I've personally seen peptide drugs lose 20 to 40% integrity simply because the internal pH dropped too quickly. You may see deamidation, oxidation, aggregation, or hydrolysis, all happening inside the PLGA matrix. Here's the key insight. Sometimes the polymer is fine, but the API simply can't withstand the microenvironment created during degradation. So how do we prevent the API from falling apart? There are 3 highly effective approaches. 1. pH stabilizers. Adding basic excipients like magnesium hydroxide, PEG, or PVA can buffer the acidic byproducts and protect the drug. 2. Polymer blends. Mixing different PLGA grades can smooth out degradation behavior and create a more neutral internal microenvironment. 3. Pre-treatments. Lyophilization or solid-state modifications can dramatically reduce the API's sensitivity to acidic degradation. These strategies often make the difference between a formulation that fails stability and one that moves confidently into clinical studies. Not all stability failures are chemical, some are purely physical. Particle aggregation is one of the most frustrating issues because everything may look chemically stable, but as soon as the particles clump together, the release profile shifts. Residual solvents, incomplete drying, insufficient surfactants, or even static charges during processing can cause particles to stick together. And as surprising as it sounds, many so-called chemical instability problems turn out to be physical instability issues in disguise. To prevent aggregation and maintain physical stability, here's what consistently works. Optimize your surfactants. PVA grade matters a lot. Consistent hydrolysis grades produce predictable particle sizes. Control your drying process. Slow, controlled drying prevents internal stresses and reduces surface stickiness. Use cryoprotectants. For nanoparticles, ingredients like mannitol or trehalose protect particles from collapsing during storage. And finally, temperature control. Even small fluctuations can soften PLGA and cause aggregation. GMP manufacturing environments help eliminate these risks. Another major challenge is solvent management. Residual solvents like dichloromethane or ethyl acetate can alter particle porosity, encapsulation efficiency, burst release, and long-term degradation patterns. If solvent removal isn't consistent, your PLGA system becomes unpredictable. This is why validated solvent removal, optimized drying, and strict purity controls are critical for long-acting injectable development. In the end, PLGA stability isn't about fixing one issue. It's about managing the entire system. The key challenges we face are fast hydrolysis, API instability, particle aggregation, and residual solvent variability. And the solutions come from smart polymer selection, controlled processing, tight moisture management, stabilizers, optimized surfactants, and validated manufacturing practices. When these elements work together, you get stable, predictable PLGA injectables that perform the way they're meant to. Thanks for watching.